In this video, we want to interpret some actual spectra and talk about what is behind all of this splitting that you see in an actual NMR spectrum. We'll also learn how to use 2D spectra to interpret and assign carbon peaks. So here's our example to start off with. We're looking at a sample, azulene. That is a 5-membered ring that is fused to a 7-membered ring. And if you look at the structure of the compound, there are hydrogens all around the outside. There's 8 hydrogens in all, but they're not all unique. So if we start here on the left-hand side, here's hydrogen 8, and it would be unique. So one of these signals down here is coming from that proton. And then, of course, 9 and 7, as labeled here, they would be equivalent. So another one of these peaks is from those 2 protons. And then, of course, we've got the pair 6-10, the pair 4-2, and then alone you'll see a signal from hydrogen 3. So count them up all together. 1, 2, 3, 4, 5. There should be 5 signals, and sure enough, we see 1, 2, 3, 4, 5 signals in the spectrum. Now there's more than 5 peaks because each signal coming from these atoms is split. We have splitting in a proton spectrum. What does that do to? Well, remember, every time we see a peak, whether it's this entire collection here or one of these individual peaks, every time we see a peak in the NMR, it's because there is a nucleus responding to a magnetic field. And so even though the nucleus for one of these protons is giving a signal, it's affected by neighboring protons in terms of the local magnetic field that it sees. So, for instance, let's pick one of these hydrogens here. If we were trying to think about the splitting pattern that would be due to this particular hydrogen, we would look at the neighboring hydrogens that are 3 bonds away. So 1, 2, 3, that would mean it would be split by this hydrogen. There's no hydrogen in that direction, but if we go 1, 2, 3, we see this other hydrogen. So there are 2 hydrogens that are 3 bonds away that will split the signal, and so that will mean that we will see 3 peaks altogether, a triplet signal for that particular hydrogen. That splitting is referred to as 3-bond J splitting, and so we would refer to that splitting. It actually has a value which corresponds to how far apart these peaks are, and that value would be labeled a 3 with a superscript, J, and then in parentheses the atoms involved. So 3-bond J coupling between 2 hydrogens is what this symbol means. Okay, so we go around the molecule here. We've said that this is a triplet, right? The pair 7-9, that would also be a triplet. The pair of 6-10, that would only be a doublet because this hydrogen is more than 3 bonds away. Say 1, 2, 3 only takes you over to the carbon 4. So this would be a doublet. Likewise, the pair H4 and H2 would be a doublet. And this last one would be another triplet. So we should have 3 triplets and 2 doublets. Sure enough, we do. Doublet, triplet, triplet, doublet, triplet. We have the right pattern. Now, which of these protons goes with which of these peaks. You have all the information you need, the splitting patterns, the integrals down below. Go ahead now, pause the video, and see if you can't make these assignments. In other words, tell me which protons go with which of these 5 peaks. Okay, so we've given you enough time to think about this. Let's work on the doublets first. There's only 2 doublets here, and so we're going to decide between these 2 peaks here. Their integrals are both 1, and so that means that they're the same number of hydrogens, in this case 2 each. Look at the splitting patterns. Here we've got a well-split doublet, and over here it looks more tight. The J value, the 3J value, is much smaller here than in here. You're comparing this width to that width. One is larger, one is smaller. So the larger one would go with the pair H6H10, because the splitting here between this proton and the one that's 3 bonds away, because this ring is open, this distance here will cause the splitting. There's a direct relationship between the distance between the neighboring proton and the value of J, and this will cause this to be a greater value. Whereas in the other doublet, you're looking at comparing these 2 atoms, and those are, H4 is split by H3, but that distance is shorter, so it's going to be a smaller J value. So that means I would assign this peak here to be the 6 and the 10. They're equivalent. And this peak over here would be the 2 and the 4. I just used a rule of thumb there about what the splitting should be based on the distance that the neighboring atom is away. Now you can confirm this with a Gaussian calculation. It's one of the nice capabilities of Gaussian in terms of NMR. You can do what's called an NMR equals mixed calculation. It will show you the splitting between any pair of atoms. And if you did that, the 610 would show that the splitting is about 10 hertz for those pairs of atoms. And if you compared, the splitting, the 10 hertz refers to the 6 and the 7, the thing that's splitting the 6, or the 9 and the 10, that would be equivalent. I'm saying that would be 10 hertz. And if you looked at the 4 and the 3, that splitting is about, let me look it up here quick, that's about 4 hertz. So a Gaussian calculation can confirm that the doublet that is a little bit wider here is the 610, and the one that's more narrow is the 2,4. Moving on to the triplets now. If you weren't aware of the whole idea of the magnitude of J, pause the video and check your work. See if you can assign the triplets properly. All right, if you had time to check your work, we can look at the triplets next. First off, the integrals are going to help us a little bit for the 3 triplets, because here we've got integrals of 0.5, 0.5, and then 1. So we know that this triplet out here in the end is the one that is due to the pair of atoms, 7, 9. The other triplets are H8 and H3. They're single atoms. And so we know without any further analysis that we can assign 7 and 9 as this peak simply because of the, value of the integral there. And we're left now with just these two triplets down here. And hopefully now, from using the magnitude of J argument, you'd be able to identify that the triplet that's more well-formed, that's wider split here, would be associated with the 7-membered ring. And so this would be 8. This is the 8. And then this would be the 3, the triplet associated with the smaller ring. There's our assignments. Look back at them. See if you agree with how we came up with that. We want to turn our attention now to the carbon spectrum of this very same molecule. And so here is the carbon-13 spectrum. It's called C13CPD. That's short for carbon-13 carbon-proton decoupled. And the proton decoupled part of this is very important because if we didn't have the protons decoupled from the spectrum, you would see splitting patterns here, just like we did in the proton spectrum. Because the protons would split the carbon signals just the same way that in a proton spectrum, the protons split each other. That's why we do typically, for carbon, we do what's called a CPD experiment. And you'll see each carbon with a unique signal. So it's a singlet for each carbon. Here I've labeled the peaks so you can see the values. We've got 1, 2, 3, 4, 5, 6 peaks here. So there must be 6 unique carbons. And that's true. It's, the same 5 that we looked at before, plus now we have C1 and C5 would be associated with one of these signals. So this is going to be a little bit harder. We don't have any splittings to look at here. And so the way in which we would assign this spectrum to, which peak goes with which carbon is we would do some sort of a correlation spectrum where we can correlate the already assigned proton spectrum in order to make these peak assignments. That's what we see here. A third spectrum, which is the HCCOSW spectrum. This is a type of hydrogen-carbon correlation spectrum. The way in which we can now assign the carbons is what appears in the HCCOSW spectrum is along the vertical axis, you see the same proton spectrum that we already assigned. And then along the horizontal axis at the top, you see the carbons, 5 carbons from the carbon-13 spectrum. Only 5 because this type of 2D spectrum will only show carbons that have hydrogens attached. So it's a simple matter now of matching up. Each of these regions here shows us how to match up and get the assignments for the carbons. First step would be to remind us of what each of these, this was the 6, right? This was the 3, this was the 8, this was the 4. I'll just pick one, even if it's a pair, just so we know which one to go on. So this was 6, 3, 8, 4, 7. So now, if we want to figure out what this first peak is in the carbon spectrum, we would go down and you see that it correlates to the hydrogen 8. So the 2D spectrum basically allows you to match up peaks for the carbons with peaks that we already know for the hydrogens. And so we would assign this one as C8, and the next one would be C3. The next one in line is C6. Come over here. This one is C7. And this one is C4. And of course, again, if there's pairs, I mean to indicate the pair as well. So this 6 would also be the 10 as well. So 6, 10 for that. This 7 would also be 9. And this 4 would also be 2. So we use the correlation spectrum to assign the carbon peaks. Now there's one peak that's still missing here, and by process of elimination we know that that has to go with the C1, C5, and so we can go back and make that assignment in the original spectrum. And so here's the original spectrum, and we now know that this peak at 140 parts per million is due to the pair 1,5. And the rest of the peaks we've already identified. Notice also that this 1,5 is smaller in magnitude. That has to do with the splitting, and you can often quickly identify the peaks that are lower as being the ones that are that don't have hydrogens attached. That's just another quick way of identifying them. Okay, so in this case we've fully exhausted what I want to say about azulene. I've discussed how to assign carbons by correlating them with the hydrogens, and I've discussed how to assign hydrogens by looking at the splitting patterns, including looking at, in case of a triplet, what's the magnitude of the splitting in order to make the assignment.